The Hangout is live. Waiting for the. It says it's live. I don't see it showing up on YouTube yet, though.
Yeah, I see it's live on the Hangouts. It's not on the YouTube. Oh, there it goes. All right, so my YouTube channel is muted now, so we don't have reverb.
Yeah.
Keith, if you have the YouTube channel open at the same time as this, go ahead and mute it so that we don't get reverb. If not, then don't worry about it. All right. So, anyways, I'm Woody or Woodson Colt from from Piazza. Mallory's here too, so we have both our TAs for this class. So we're here to do the midterm review, and I have some tabs open that we can go over basically anything. I have all the practice problems open, the midterm review open, and the key concept sheets from weeks 1, 2, and 3. And then we welcome any questions that you have, and we'll try to answer them in real time. So, Mallory, you want to introduce yourself real quick?
Hi, guys. I'm Mallory, another one of your TAs, and I as well have the tabs open and anything. I have some paper. If we need to work out some problems for you, we can do that as well.
All right. So I'm going to go ahead and present my screen so I can show all my notes. And Keith, the floor is yours now. Start giving us some problems to work or asking questions. I really enjoy conceptual questions, but we can work through some math problems as well. And also, I hope you've had a chance to watch our previously recorded video from semesters ago. That's the video where we go through literally every single problem from the midterm review. We're not intending on going through every single problem in this session right now because we've already done that. We just want to answer questions that weren't quite covered in those previous videos, if possible. All right, so my screen's sharing are presented now. So Keith, if you don't have a microphone, since I haven't heard you talk yet, oh, I see your message now. So okay, I was gonna say you have the group chat there if you want to be able to talk to us if you don't have the microphone. I don't know, Keith, are you getting equipment or something, or?
Oh, we lost Keith.
Recorded forever on YouTube Live.
They may be switching computers or rebooting.
Yeah. Well, I mean, I feel like I could just talk for the sake of talking, but nobody's really watching right now, except for the people in the future.
Hey, I guess my biggest thing was I wasn't actually expecting to start off by asking questions, so I didn't really come prepared to ask questions right away.
Uh-oh.
So I was trying to come up with a question to ask. I guess.
Okay.
That's the thing.
Well, if you don't have specific questions, that's fine. We can maybe start at least with what general topics you'd like us to
Can you guys hear me, or?
Yeah, I can hear you. Can you hear me?
Am I muted?
No, we can hear you. Can you hear us?
Yeah, I can hear you guys now.
Okay.
Like, my problem is like, I seem to understand it when like when I see a problem, but then when I like get a problem in front of me, I can't figure out where to start. Like, I get confused between like the K's and the T's, and it seems to like end up going in a circle.
Okay.
I guess I'm not quite sure
So I can go ahead and
what my issue is. I guess
I can explain maybe with like a list of variables and just give a brief description of what each type of variable is used, or at least the standard way that we use it in this class. So I don't know if I maybe open up Word and I'll just type as I talk. Well, I'll make a list of all the variables I can think of. All right, so I'll do T and N. Whoops, I don't want it to auto capitalize. I just want lowercase. All right, N, so that's easy. And then, well, I wish this might not be as easy. Actually, I know what I could do through Word. Let me pull up Piazza, and I'll just make a fake post without.
Like, I guess one question is like, with causality, it sounds like earlier we were defining it as like, if the current value does not depend on future values, it is causal. But then later on, we define it to be if like the function is 0 if t is less than 0, it is causal. Are those two things linked, or am I messing up on that like concept?
Okay. Yeah, let me pull up the. So I have the notes here that define them. Let me just have the YouTube channel maybe open. All right. Anyways, with causality, yeah, there's different ways of expressing the same information, and it sounds like you just saw two different definitions that say the same thing intrinsically. So causality, in the normal human sense of the word, yeah, one thing leads to another. You have a cause and effect. And so when we look at, or when we build systems, they must be built in this real world, in the physical world. And the world that we live in is causal because of, the chain of events lead from cause to effect, and not in reverse. So when we mathematically say that, we say that a system must be 0 for anything to the right of the y-axis, for any t that is less than 0. So so let me find the other way that's written and see if I can explain it from a different perspective. Thanks. Okay, yeah, so here's the other definition of causality. If y of t depends on x of t in the present, and x of t, or x of t minus t naught for t naught in greater than 0 past. So this one's a very confusing statement here. Just me saying it out loud, I stumbled on it several times. So I can understand how this one is confusing. But what this means, what this saying is, it's looking at the same concept of causality, but from a different perspective. So when we have, let's say, a piece of test equipment that we've built in real life, like, I don't know, a Spec A or something. Have you worked with Spec A's or oscopes before? Perhaps in the Circuits 1 class or somewhere else, maybe in industry? Well, I'll just keep going. So anyways, from the perspective of a piece of test equipment that's operating in real time, it is collecting data in real time and storing it in some kind of buffer, in some kind of memory inside of itself. When it plots this on the screen, on the scope, the x-axis typically is time. It's plotting it and then moving forward in time, but the axes are centered on the scope screen itself, just for the human's readability. So if you can imagine, from the scope's point of view, positive values on this t-axis go to the right, and past values go to the left. But when we look at it mathematically on a piece of paper, and you're drawing out your axes, it's kind of the opposite. Does that make sense? So RT depends on activity.
It looks like he's asking about a question on week 1 homework.
Okay, 1.27F from week 1. Let me pull that up real quick.
Also, for both of those descriptions of causality, they kind of are linked together, saying the same thing. One on week 1 is telling you that if it's like what he was saying, a function that's defined on the right-hand side of the y-axis, then it has a chance of being, it has that possibility of being causal. Sorry, I can't speak today. And then if you go and look at that second one, on week 2 key concept, it's basically just telling you that in order for that to happen, anything on the left of the y-axis needs to be 0.
So I have the homework problem, the practice problem that you have. I have it here.
All right. So like, if week 2 statement is true, week 1 statement is also true. Like, they're kind of saying the same thing, and either test will prove causality, I guess.
Yes. So these 2 definitions for causality are talking about in the time domain. Later in the course, we'll learn the same definitions, but in the frequency domain, and it's actually easier to work with or understand in the frequency domain. So look out for that after the midterm. But basically, whenever a signal, well, this is for Laplace transfers, which is the last week of the course, the last 2 weeks of the course. If a Laplace transform includes the y-axis, then it's causal, and that's way easier to like determine, you know, when you're looking at a problem, than these time domain expressions. So causality, conceptually, I guess or not conceptually, but like when you're looking at a problem in front of you on a piece of paper, will become easier later in the course. But I guess that doesn't help you for this midterm that's coming up tomorrow, or yeah, tomorrow. So, but just remember that anything on the positive side of the axis, if the system starts at 0 and goes off to the right side, to the positive side, then it's causal, you know, in the time domain. Now for this problem 127F, causality, we're looking at, well, I wanted to pull it up in my textbook to read it out loud. All right, so in this chapter, we introduce a number of general properties, in particular, blah, blah, blah. Determine which of these properties hold and which do not hold for each of the following continuous time systems. Justify your answers in each example. Y of t denotes the system. Oh, okay. Anyway, so F is y of t equals x of t divided by 3. So first off, I'd like to note that this is not x times quantity t minus 3. This is x as a function, and the argument of this function is t divided by 3. So that's different than the normal algebra that we see. So in mathematics, or like mathematicians, the verbiage that they use, you have an implicit definition and an explicit definition of any given function. You know, in algebra courses and the early calculus stuff, we sometimes refer to a function as f of x instead of y equals. The thing after the y equals, y equals x plus 3, the x plus 3 is the explicit definition for y. And you could also write that as f of x equals x plus 3, where f of x is the implicit definition of that, that expression. So in a general sense, implicit means it's the name of this thing, like I'm calling it x, f of x, or in this case, I'm calling this function x, or I'm sorry, looking at my screen here, I'm calling this, oh, it's not written here. Okay, anyways, I'm calling this y of t equals x with the argument t divided by 3. So that is, I just want to point that out. This is not saying x times the quantity t divided by 3. So there's a difference there. Anyways, now that we know that, we can see that y of t equals x quantity t divided by 3 is referring to an arbitrary function x. We don't know what the function x is. All we know is that we've changed its time axis by a third. So we've shrunk it, right? Okay. No, we expanded it. We made it longer in time. So to determine if this is causal or not, well, if all we've done is shifted the x-axis, the time axis rather, but we haven't changed where our starting point is, we're not taking any values at a negative point in time, this should be causal. So let me read this answer here and make sure that I just said the right answer. So for any t less than 0, y of t depends on a future input. For example, if t equals -3, you would plug that into this expression. Y of -3 equals x of -3 divided by 3, because you just plug that in for the t value. This value here was the t value. T equals -3. And then that makes the x expression negative, which is below 0. And the definition of causality is that your argument is above 0, is positive. But here we've just disproved what I said earlier, and this is not causal because it depends on a negative value for t. Does that make sense?
You're basically looking for plugging in any random value, and in this case they chose -3 because it made it easy to see it turns into a 1. There was no difficult fraction there to figure out. Mm-hmm. But any value of t less than 0, is it going to give you a positive value of that function? If it does, then you're causal. If it doesn't, you are not causal because of those definitions of causal where it has to depend on the present or the future, or the present or those future values.
So with this example, if we had maybe inside the parentheses for the x, not t divided by 3, but instead quantity t divided by 3 squared, then even when you put in negative values for t, it would result in a positive value, and thus that system would be causal. But since we don't square it here, or we don't have an absolute value of operator, or anything else that guarantees that this output would be positive, this particular system, there are cases where it produces a negative, and thus it's not causal. Does that clear it up for you, Keith? So for Dawn and Michelle, who joined just a little while ago, so Mallory and I are here to go over not go over the midterm review, but we're here to cover gaps from the previously recorded video that I posted earlier this week. Feel free to, while Keith is typing, it just looks like he typed some more. Anyways, feel free to ask us questions, at least when there's gaps between us talking, and we'll do our best to answer them. So let's see what Keith said. When it comes to convolution and systems that are made of multiple integrals, how to figure out how to write them out. For example, 4 on the review sheet. So let me go to the review sheet.
And guys, if you have questions while we're talking or while we're explaining anything, feel free to type those out like Keith's doing. That way we don't go too far ahead and not notice you have a question.
Okay, so on problem 4, it's a convolution problem. The impulse response of an LTI system is given by h of t. What is the output y of t when the input x of t equals a couple unit steps? And Keith is asking, when it comes to convolution and systems that are made of, how do you figure out how to write them out? Well, for this one, you don't have multiple integrals. You have one term here, and these 2 terms become your limits of integration for this one integral. So not a very good example for what you want to see us breaking it out into multiple intervals. But let me look at how I solved this problem, number 4. So I did all the even problems here, so this one should be right here. All right, so the impulse response is this. Oh, I see. It already has a unit step there. That's why we'll have to break it up into multiple intervals. So we have 3 unit steps here. All right, so this unit step on the h of t, it just simply tells us that this system is causal. Remember, whenever you see h's, that means a system. Whenever you see x's or y's, that means the x's are inputs and the y's are outputs. That's just the standard notation that we use. So this system says that this system only works when we turn it on at t equals 0. It doesn't depend on any negative values of t. So just going back to causality we were talking about before. Now after that, if the input is x of t is the unit step minus the unit step shifted at 2, this is just a single pulse. This is just a little square wave. Only one pulse too. It's not even a train of pulses. So what is the output when we put it through this system, this exponentially decaying system? So to figure that out, we do a convolution. So here I've just written the expression for convolution, and then I wrote the definition for convolution, which the definition just says that we replace our t's with tau's. That's the change in variable. We're doing this integration with respect to tau, so that's why we're changing the t's to tau's. And then you take your second function and you time reverse it, which just means that you flip it about the y-axis. So now, let's see what I wrote here. Hard to understand and visualize convolution in the time domain, but it's easy to understand in the frequency domain. It's simply the product of h of j omega and x of j omega. So what you would do is we haven't quite learned this. We're going to learn this after the midterm, but you could just take the Fourier transform of these 2 expressions, and then you just multiply them. But we're not going to do that now because we need to learn how to do convolution in the time domain, because that's what's going to be on the midterm. So I continue on doing it the proper way for this point in the semester. And I've rewritten everything, but now I've rewritten it to have what the problem gave us. So here's x of t, or what became x of tau. And then here's your h of t. And we have time reversed it by introducing this negative tau. So remember, we're doing this convolution with respect to tau. Time reverse a tau, you just put a negative in front of it. You don't have to mess with the t. The t is a constant from the perspective of the integration. All right, so now we just split and simplify. So this is where Keith's question is going to be answered. So basically, I'm going to rewrite this without the bracket, or by distributing. So you can see here we have brackets, a grouping of brackets here and a grouping of brackets here. So the first step is you just distribute via normal algebraic means. So this term times this term, and then this term times this term. Wait, I'm sorry, there's no plus here. So it's this term times this term, and then this term times this term. Sorry about that. So that's what I've done here. So what's E2 quantity t minus tau unit step times this quantity here, or times this unit step here? Well, it just becomes, I just write it out like that, then next to each other. Mind you, I haven't figured out my limits of integration. I'm going to do that in the next step. Now, what's this quantity times this quantity? Well, we have this negative, and so you just multiply them together. I took the minus sign and I put it out front of the integral, because we can do that. And then we just get this expression here. So that's how you split it into 2 integrals. Now, the next step is to figure out our limits of integration. The way you do that is with the unit steps. So each of these separate integrals has 2 unit steps in it. So this one has this unit step and this unit step, and those become the 2 limits of integration. And then this one has this unit step and this unit step, and those will become the 2 limits of integration. So this is how you actually do that. To find limits of integration from the unit steps, well, with this first integration, we know that this unit step here, this first one, is just a regular unshifted unit step, and so it turns on at 0 and stays on until infinity, you know. So that means that we will be integrating from 0 to something, and so that becomes the lower limit. Now this other one, u of t minus tau, we don't have numbers in here, so it gets a little confusing, but it's really the same thing. What did I do? Well, let me read this note here. U of t minus tau is just a delayed step pulse where the delay is tau. We don't know what tau is because, you know, it's going to be varying throughout the integration process. We're going to be moving it. And so you just simply write as your limit, well, what does tau become? It becomes t. When you finish this integral, it becomes t. Let me see if I can figure out how to say that better so it makes more sense. So after you've done the actual integral, you know, what's the integral of exponential? It's going to be the exponential times, you know, the inverse of whatever its exponent was. Then you plug in your, you know, you plug in your limits of integration into wherever tau pops up, and that's going to, well, I'm still not explaining it very well. I should have reviewed my video to see what I said before. Anyways, this tau is going to become t eventually. So anyways, we can just write tau or t as our upper limit of integration because we know that that will change as we're going through this integration. Now, for the second integral, we're basically doing the same thing. Now, this unit step, the u of t minus 2, is a little bit easier because we have an actual number. So we know that if you draw this on a graph, it's going to look like this. It's just a unit step shifted over by 2. And so we know that the lower limit is going to be 2 because we can't, everything's 0 below 2. So we start at 2, that's our lower limit, and we go up to infinity, as you can see here. But infinity, well, we have to put something in for infinity, so it's going to be t again. Because we know that this integration going over tau will eventually have the t be plugged back into it after you finish the integration. So anyways, that's how you get your limits of integration from 0 to t and then from 2 to t. Now you can actually do the integration. So to do the actual integration, we need to simplify, you know, these portions here. We have you know, a summation. So that means that we can remove anything that appears to be a constant from the perspective of the integration. And right now, that's going to be the t's, you know, and any other constants that you might find. In this particular problem, we only have one constant from the perspective of the integration. And so the first step to do that is distribute this 2 to each of the t and the tau. Once you've done that, then you can use the exponent rules to simplify. And just a reminder what the exponent rule, the product rule of exponents is whenever you have, this is how we see it in homework problems, so I'll say it backwards. Whenever you have a base with an exponent that has, you know, addition or subtraction in it, you can split them like this, where you have the same bases, but they can be multiplied out. And what this allows you to do is if, let's say you're doing an integration and this is a constant and this is not, this is your variable, well, this constant can then be moved outside of the integral, and you don't even have to worry about it at all. And so that's exactly what I do here. After I've distributed this 2, it becomes -2 plus 2 tau, -2t plus 2 tau, and thus I can rewrite it like this. And then this portion can be moved outside of the integral. And that's why it benefits us. Yeah, this is just me reiterating what I just said. The t is just a constant from the perspective of the integration. And this is what our integral turns out to be. And this is basically a trivial integration. You know, the integral of an exponential is the exponential. So I've rewritten my 2 integrals here's the first one, and then here's the second one. And then from there, you're just doing normal calculus, normal integration. So, you know, here's what that integral turned out to be, 1/2 times the exponential, and then you evaluate at these endpoints. So I just plugged in, you know, t and 0, you know, just like that. We know that an exponential times to the 0th power is 1, so there's the end result there. And then for the second integral, we did the exact same thing. Here's the rewritten form. We did the integration of an exponential. It's very simple. And then you evaluate at these limits here, plugging in t and 2. This just becomes a simple number, which I've equated here. Or, yeah, this is just a simple number, which becomes, becomes this part. And then I distributed this part, which is why you see that there. All right, so the last step is to put it all together. And since we started with a summation of integrals, there's a minus sign, but you then just subtract them from each other. And you generate a piecewise function. So your piecewise function will follow the limits of integration that you determined early on. So we have 0 to t and then t to 2. So basically anything less than t, or when t is less than 0, we had, you know, basically a 0 result. And so you can just put that into your piecewise function. This function, this output is 0 for any time t is less than 0. Then from 0 to 2, that's when all of our magic happens. And that is, you get this result determined by the, you know, putting it all together by, I think, this step here, you know. So my result for the first integration minus my result for the second integration became, after all the algebra, became this right here. Well, when you have t between 0 and 2. Anything that has t greater than 2 is going to be the full expression. And that's why I have this 4 here. Yeah. Hopefully that answers your question, Keith. I know I went into a little maybe too deep, but yeah, the real key to this piece, I've been talking for a while, but the real key to this piece is how you manage your unit steps and how they become the limits of integration. Anybody have any other questions? Don't be afraid, John. You know, there are no silly questions here. That's what this review is for. So let's hear them. You know, we're not going to make fun of you or anything like that. That'd be to leave us. I assume, like in the Piazza, that's where these questions came up. Did we cover them well? Did we answer those questions in Piazza?
John, if there's any specific like problems we can help you with to kind of clear up those questions you may still have, or any specific questions you may still have, feel free to ask those because we can definitely help out with that.
And also, if you know, if we're waiting for questions to be able to answer, you guys don't have to type out your questions. You can if you feel free to unmute your mics and talk to us. Maybe it'll be more natural to ask a question. If you want to type, that's perfectly fine too.
John, for that question on the basic math and calculations, if you go to Piazza, Woody had added a link to some really nice cheat sheets for kind of those older skills that we had worked on in the past that a lot of us, if you don't use it, you tend to kind of forget how those worked. And those were amazing resources. I think Woody's pulling those up right now. You can download those. They're PDFs. A lot of the professors use these ones as well to kind of give you a reference on that stuff if it comes down to that.
Well, it might be a little difficult to find now.
Let me find where it was.
I can just pull up the original link too.
It's on the 3.3 trig difficulty, or 3.30 trig difficulty post. Towards the very top.
The 3.3 trig.
3.30.
Oh, 3.30.
There you go.
Okay, here it is. So here is a link. Well, this is a better link because it'll give you the cheat sheets for all types of math. This will be for algebra, Calc 1, Calc 2, I think even Calc 3, and trig. Did I mention trig already? And they're great resources. So one of the ones I use the most, I think, is the trig one because it has all of your trig identities. And sometimes we pop up on a question that might require a trig identity. For example, I think this post here in Piazza was asking a question about how do you simplify when you have a sine times a cosine, like a single term sine times cosine. And the way you would do that is by using the trig identity. Let me just pull it up, where it breaks it off into a single trig function. It's gonna make me download it again. I already have them downloaded. Oh, whatever. It'll be faster if I just download it again. All right, so let me zoom in so you guys can see it bigger on your screens. And then I'll scroll down. And this has everything you could ever think of for trig, including the unit circle, which is neat. Well, no, not, oh, here it is. Yeah, this unit circle, so you can, every math teacher, every trig math teacher said memorize these. I personally never memorize these. I just plug them into my calculator again whenever I need them. But anyways, if you don't want to plug them into your calculator or your calculator broke or the battery's dead, this is a great resource for that. And then here's the trig identities. Specifically, the trig identity that we're working on in this Piazza post was a sine times a cosine. And in terms of Euler's identity, you can use Euler's identity on this. You're just going to have, your normal expression for sine with parentheses grouped times the normal expression for cosine, and then you would just FOIL it, and then it becomes a big complicated mess. Or you could just skip that, go straight to this trig identity, and then do Euler's for this and Euler's for this, and then you have a simpler expression without as much scratch paper. You won't need as much scratch paper doing it this way. So that's why you might want one of these cheat sheets. I have these cheat sheets saved on my computer, on my desktop, and a lot of exams these days allow you to open up new PDFs. For this class, I don't think it will, but future classes it does. And you can just pull this up and then use it during the exam. Now for this class though, you can't pull this up and you can't print this. You only get one sheet of paper for notes. But I will just write down the most commonly used from this sheet onto your personal cheat sheet. The most commonly used ones might be these product of sum formulas, maybe even these double angle formulas. But honestly, you can get through it without writing any of these down if you just use Euler's formula. Keith asks, when it comes to the exam, which formulas are the most valuable? So in terms of the cheat sheet, I wonder if I scanned my cheat sheet. So the professor doesn't like when we give our cheat sheets out to students, because students should be making their own cheat sheets. But typically what I did, or what I did on my cheat sheet was I wrote down a lot of these definitions for things from each of these three key concept sheets, which are all on Canvas. Honestly, I would never look at the textbook. I would never look at the lecture PDFs. Well, you can if you want, but the greatest resource, in my opinion, is these key concept sheets, because everything is consolidated and neat and organized. So some of this stuff will be provided to you on the test, on the exam, but not all of it. So I would go ahead and write down these definitions, these definitions for continuous time and discrete time for all of these things. Write down definitions for these, what makes a system invertible, what makes them causal, stable, so on and so forth. What you don't need to write down, and I will verify this in a minute, are these tables. You don't need to write down these tables because these tables will be provided for you on the exam. So don't write those down. What you could write down from these tables, though, are maybe examples where one of these properties are used on a problem. And there's nothing wrong with that.
And to piggyback on that, when I was doing, any type of cheat sheet, this class, any other class that I'm taking or taken, I always like to kind of, especially if you're given that front and back side, that front side, put those equations down, like what he said, from those key concepts. And I always like to use at least a portion of that back side, if not the whole thing. Work out those problems that you are kind of iffy on, the problems that you needed a walkthrough on there, because I mean, a lot of people going to go into that test, they see something they're not quite sure about and they panic, and that panic mode sets in and you forget things. So it's kind of nice to have those quiz problems or things like that worked out on there as kind of a guide. If you get lost, if you get into that panic mode, it's really nice to have that as an example to kind of look through. And on Keith, on your next question where you're asking about those trig formulas, I would definitely look at the ones like Woody was showing, that sine times cosine one breakdowns. A lot of that should be a majority of the ones you're needing. Any of those trig formulas you've kind of had to look up while doing homework problems, those are the ones you're going to want to put on there, because if you've had to look them up, most likely going into a quiz or an exam, they're not going to stay that fresh in your head.
John asked, the limit interval was for practice 322A. So let's go to practice 322A. Oops, I just skipped it. So here's 322A. See what the problem was even asking for. So I got the textbook in front of me. I gotta flip to that page. All right, 322A. Determine the Fourier series representation for the following signals. And we're doing an x of t that we have a picture here of a sawtooth wave. We're doing A, right? No, we're doing figure D, I'm sorry. Figure D, the next page, is not a sawtooth wave. It is a series of direct deltas, a series of spikes. So with this problem, we know that right away, without even doing anything else, we know right away that we can use the sifting property of direct deltas. And just to review the sifting property, so the sifting property is when you have a direct delta during convolution. The sampling property, which was first introduced in week 1, but will be really important for after the midterm. Anyways, I'm getting on a tangent. The sampling property is for the time domain when you're just multiplying direct delta times a function or times a thing. The sifting property for this problem that you wanted me to work on is convolution, so we have to use the sifting property. And that says that whenever you have anything, a function, times a direct, or I'm sorry, convolved with the direct delta, it returns that thing. If your direct delta is shifted, then when you have a thing, a function of any kind, convolved with a shifted direct delta, it returns that same thing, but shifted at the same amount as the direct delta. And so that allows you to greatly simplify problems when you're working with, direct deltas and convolutions. So back to that homework problem, that practice problem, 322A, figure D. So I don't have the picture here that you guys can see, but you have a direct delta centered at 0 with 1 amplitude, and then a direct delta centered at 1 with -2 amplitude, and then that pattern repeats over and over again to infinity. So when we go to look for the Fourier coefficients, we only need to worry about one period of this signal, and so thus those two points that I just mentioned, 0 and 1, are the only ones that matter. All the other ones we don't care about, because we're only going to do this over one period. So first, let's determine the period, and that you can do by looking at the picture, and clearly it's 2, and so that's written here as 2. Then you figure out your angular frequency by taking the inverse of that and multiplying by 2 pi, of course, and it comes out to pi because the 2's cancel. Anyways, that part is trivial. The next part is actually doing the, applying the definition for Fourier coefficients. So let me pop over to the week 3 concept sheet. And well, first, are we working in discrete time or continuous time? We're working in continuous time. Yep. So anytime you see an x of t with round brackets, or what we call parentheses, that is continuous time. Anytime you see square brackets with an n instead of a t, that's discrete time. So this one, we're working with continuous time. So on the key concept sheet, I'll look at the continuous time side, which is usually the left side. Where this problem wants us to find the Fourier coefficients, which we denote as A of k. And so thus, I'm going to use this definition here. This little t here proves that we only need to worry about one period. And then all you're doing after that is taking an integral of your signal times a complex exponential, a decaying complex exponential. So back to the problem. That's what they wrote here. It's just the definition of finding the Fourier coefficients. Then we plug in our limits of integration. Since we're only going over one period, you can choose any period you want. You could go out to, 237 and, 239, but that would be ridiculous. We humans tend to stay towards the origin because it's convenient. And so to include the entire signal, we just go out a little half measure envelope outside the signal itself. In discrete time, there are no half points like this, but it doesn't matter because at -0.5, your signal is 0, so who cares? And then your top one is at 1.5. And the reason why we do this is because this covers a full period of 2. We know our period is 2, so we need to cover the full period of 2, which we do.
Woody?
Yeah.
So I guess that's really where it kind of made my brain freeze up, was knowing that it was with the impulses, it made it discrete, even though it's in continuous time. It didn't make it discrete, but it appeared discrete. Using the half integer, halfway between the integers, is really what kind of froze me up, because I was like, well, why didn't you just use 0 to 2 or some other range? Using the half, it's like we know that it's 0 at those points. Is that preferable? Is there some logic process for picking that, or was that just to show you can use any number?
So yes, there is some logic process behind that. So I'm going to go ahead and pull up a picture. Now, the direct delta function is in terms of mathematicians, it's a very hand-wavy, magical thing. It's not it is well defined after you've defined it, but by default, it's not very well defined. I don't know how to describe it. It's a unicorn. Anyways, we define it as humans intuitively as just a spike with an infinitesimal width and infinite height, such that the area under this is 1. How do you have an area when you have an infinitesimal width? So that's the magic behind it. It's very hand wavy. And the way you more clearly define it, if you need it, is by doing this little thing here. Does everybody see this GIF? Let me zoom in. So this is what a direct delta is you're taking an infinitesimal width that goes down to 0 eventually, but you can't quite make your limit of integration 0 because you can see that this is symmetric around 0. And technically, magically, somehow, you're going to be skipping off you're lobbing off half of the area under this curve. And so, thus, when we take our limit of integration, we want to not have to deal with this technicality by just making our limit far beyond the infinitesimal length or width of the direct delta. Does that make sense?
So by not having it match up with the impulse, it actually makes it more accurate for our mathematics?
Yeah, it allows you to include the entire direct delta, because you know the direct delta is a symmetric curve that we refer to as a spike. But yeah, if you just went straight at 0, you can see that the left side of here would be cut off, and thus you'll only have half of the area under the direct delta when you take the integral, and it would mess up your math. Technically, it would. So yeah, that's why we extend it out like that. And you're exactly right. I guess I was misspeaking earlier when I said, you know, there are no half measures in discrete time, but we're not working in discrete time. You're absolutely right. We're working continuous time. And yes, x of t will be defined at -0.5, but the direct delta will not. The direct delta will be 0. And thus, when you multiply whatever your signal is at this point, when you multiply the signal times the direct delta is 0. Therefore, who cares what the signal was? It will also be 0 at this point. And so the direct delta, as you already said, kind of discretizes. That's a weird word to say. But yeah, it discretizes the continuous time operation, or the continuous time problem.
I would say that that's definitely something I'm going to have to go back and try to review, just the mathematics of, hey, here's how you deal with direct deltas. I've kind of squeezed a second question in there that I was curious about.
Okay.
And that had to do with 3.1. And that was in the converting of sine to cosine. I seem to remember that, but when I was looking at the impulse or the trig sheets, I could only find the reference to pi half minus u, not the u plus pi half conversion. And I was trying to figure out, can you help explain to me or remind me how that works for trig, as far as, hey, you can do this and go for it. You won't
Yeah.
run into trouble.
I don't know if anybody has a good website to just graph. I have my graphing calculator in front of me, but you guys can't see it. I wanted to be able to plot something. So maybe Google will be my friend and something will pop up really quickly. So sine of, I'll call it x. And then I'm going to add another expression, cosine x. So you can see that sine of x and cosine of x in trig terms. The red is the sine, which we all know starts at 0, goes up to 1, and it goes back down. The cosine starts at 1 and then goes down to 0 and goes back to, and then continues on. So you can see these are the exact same curves, but one is shifted by a uniform amount from the other, and that shift is 90 degrees. So if you write this out mathematically, you would say that a cosine is equal to a sine plus a 90-degree shift. And the way you write that on paper is cosine, well, I'll write it this way. Sine of t plus I'll just call it phi. I'll just use a p for phi, because it's word and I can't put Greek letters in very quickly. Equals cosine. Actually, I'm sorry. This p is going to be 90 degrees, so I'll just say 90 degrees. Let me use x's. So that's the expression. That's how you convert. Now, when you're using Euler's formula on this, when you plug in I wish Word would stop auto-capitalizing. J omega, just use a W. That equals, we know that by definition, that equals sine. Oh, cosine. Oops. And thus that allows us to derive that a sine of x equals 1 over j. What did I do here? E to the plus e to the. Sorry, this is taking me a little while. I'm sure this is written down already on one of the homework sheets or something. Anyways, so
if you look at the week 3 key concepts, those are written down for you.
yeah, probably right. Well, I wanted to manipulate it in real time, but yeah, there they are. All right, so if you have a sine and you want to convert it to a cosine, or vice versa, if you have a cosine and you want to convert it to a sine, all you have to do is add or subtract 90 degrees. That's it. And so when you're using Euler's formula, by the product rule for exponents, you can just literally add the phase shift, which is 90 degrees. That's what I wanted to show in real time. Actually, I think there is a problem that includes that on my notes. So if you guys can bear with me, maybe I'll find that. And then then I don't have to type everything out in real time. Here it is. Problem 8 on the midterm review. We can see that we have pi over 4 is 90 degrees. You know, if you plug that into a calculator and convert from radians to degrees, that's 90 degrees. Wait. No, that's pi over 2. I'm sorry. Oh, man. Okay, so later in this problem, I said, well, what if this was pi over 2? What could we have done? It would have simplified the problem a lot. And here it is. Nope. Man, I promise I have a little note that says, what if this was. Well, I can't quite find it right now, but doing converting from sine to a cosine is the same. Even if you have other types of shifts, you just have to account for that shift still when this becomes a cosine. So the first step you want to do is use Euler's formula, and this whole thing becomes the exponent of your exponentials, except for they become complex as well. You add a j in there, and that's what this here does. So here's where I wrote that. So if you have a sine of something, and let's say that something is really just something else plus a phase, you just directly plug that into your exponent, just like I've done here. And then via the product rule of exponents, which is my next note here, you can then see that your phase not having your independent variable in it just looks like a constant, and you can just put it out front along with the other constants. And so that's what I did here. Remember in the original problem up here, our phase was pi over 4. Well, using the exponent rule, the product rule of exponents, I just broke this up into exponential times an exponential with different exponents, and that's what is done here. So that is where if you had no weird phase shift, or if you wanted to convert from a sine to a cosine, this is where you would add the 90 degrees. You would say j pi over 4 plus pi over 2, and then simplify that. And then this whole result will eventually lead you to the cosine, if that's what you're trying to convert to. Does that make sense?
Yes. I was curious if at the same time you could just skip some of that and go straight from sine to cosine by adding the phase of 90, and I think that was what you were just doing there at the end.
Yep, yeah, you can absolutely do that. So if you prefer one sinusoid over another, yeah, whatever the phase is, you just add 90 degrees. Now, you have to keep in mind what direction you're going, and that's, let me pull that picture back up. If you're going from a sine to the cosine, you actually need to subtract 90 degrees, because it actually doesn't matter which way you go. Well, no, it does matter. You need to subtract the 90 degrees from the sinusoid, but if you have a cosine and you're trying to convert to sine, you would add the 90 degrees. Oh yeah, it's right here. So let's see if that is on this trig cheat sheet. It should be. I must have skipped it somewhere. I know other cheat sheets out there on the internet does have that. If you want to convert from a sine to a cosine. Honestly, though, the only times when it will be useful or helpful to convert from a sine to a cosine is if you have a sine with a zero shift and you don't want to deal with that complex number that's in the definition, or that's in the Euler's form of the sinusoid. You can go use a cosine. Or if it allows you to match up with other terms in that expression. But other than that, there isn't really a whole lot of need to convert from a sine to a cosine or vice versa. All right, Michelle has a question. Is your answer sheet posted somewhere? This way we have an explanation as we work through these. My answer sheet, which answer sheet are you referring to? Are you talking about my midterm practice, this one right here?
Yeah, that one.
So I can post it. In fact, maybe I'll post it right now on Piazza. And that's where it'll be available, and everybody can download it or view it. This is the document that I use when I explain these problems in my other video that I posted earlier this week. That means James go through. So yeah, there's a lot of notes on how I solve these problems.
Yeah, that looks to be very actually helpful, especially with us that are struggling with the math that haven't had it in years, to kind of bring back those concepts pretty easily. Yeah,
that's what I try to do, is bring it back to like, well, this little technique from algebra helps you here, you know, that kind of thing.
Yeah.
Yeah, have little chat bubbles. Anyways, yeah, let me post that real quick. And while I'm posting, hopefully we'll get another question. Here it is. And I'm going to post it on the midterm exam review session area. So like, I'll post it right here.
Hey, Keith, on your question for 2.23, why is it a function and not just points? Are you talking about why is y of t a function? I just want to make sure I'm understanding your question. Yes, okay. Give me a second to pull all that stuff up.
Hey, what do y'all send your mine so you can post it too?
What's that?
I will send you mine as well so you can post it.
Ah, makes sense. So homework problem 2.23. Let me go ahead and pull that up.
Yeah, thank you, Eddie. I was just about to ask you to pull it up.
I'm
going between too many different screens.
Gotcha. So 2.23, that implies that's week 2. Homework, week 2, homework solutions. I assume everybody has turned in their homework at this point, right? But here's all the answers. I'm going to scroll really fast so nobody can copy them. I'm just playing around, guys. 2.23.
It should be one with it looks to be a triangular function there, right there.
Are we working B or is there an A?
A was a practice problem, but I think B's fine. His question right now is when we take it's convolution, when we take the convolution between the two, why does it come out as a function? I just couldn't explain anything with, or look at all of it, flipping between the book and this page.
Right.
So now I can look at both.
Okay, so with this problem, I guess I will start at A.
A is on a practice problem.
Okay. I gotcha. All right, so
that was my same issue.
Let me flip to that page in the textbook too, so I can read the whole problem statement. All right, 223B. All right, so let H of T be a triangular pulse, and let X of T be an impulse train, which is just a series of direct deltas depicted in the picture. Determine and sketch your output, which is the convolution of that triangle and those impulses. So with this system, or with this this problem, you're convolving a series of spikes with a triangle, with a single triangle. Now, via the sifting property, we know, and that's what's written here. Luckily, I don't have to flip screens. Via the sifting property, if you can convolve anything with a direct delta, it returns that anything. If you convolve anything with a shifted direct delta, it returns that anything at that same shift. And thus, before we even look at the math or do anything on paper, we know that our output will be this triangle at centered at each and every single one of these spikes. So this triangle, copy and paste to this point, this triangle, copy and paste to this point, and this point, and all of the other direct deltas off to infinity. And that's all you have to do graphically. Very, very like simple and straightforward in that sense. Now, the only complication is when you start adjusting the period between direct deltas. So let's examine the period, the length rather, of our triangle pulse. It's it's a length of 2. We're going from -1 to +1, so it's a length of 2. So it becomes really tricky when our spikes, our direct delta spikes, reach that barrier. Because right now on this particular problem, if I copy and paste this here, we're going to be going from -1 to 1. And then when I copy and paste it here, we're going to be going from 3 to 5. And over here from -3 to -5. And then at this next one that's not, that's not in the picture, but we know it goes off to infinity. Maybe it's at 7 and 9, multiples of 4, centered around multiples of 4. So when we adjust the period between spikes down to the length of the thing we're copying and pasting, these triangular pulses will start nudging up against each other. And then if we shrink our period between pulses smaller than the length of the triangle, we start overlapping triangles. Now, when you overlap triangles, you're just simply adding up their amplitudes at every single point. And thus, if you overlap them enough, you'll just get a straight line. If you overlap them at just the right period, they'll partially overlap and add at those overlaps. And where they don't overlap, they'll just be the regular spike. So
it continues to repeat on that period. So there's the -1 to 1, the 1 to 3, and then on the next part of C where you have that 3/2 gap, it's larger than that width. So you're going to have this flat portion where you've plateaued, where you've hit not necessarily a 0, but a constant value.
Yeah, you can imagine where these flat lines are is where, if you can imagine the triangles going down to the t-axis, this triangle goes down to 1 on that side and down to 3/2 plus a half, I guess. So down to 2. And then this triangle goes down to, to this point right here, whatever that is, and down to this point right here. So anyways, where they overlap, they add. And that's why you get the flat line there.
So when I was going through these, I always kind of found it easiest to put all those triangles in, have those cross portions where, like Woody was just trying to show you with the cursor, and then determine what happens there as far as the adding goes, and then erase down through what the function actually would look like. But it kind of made it easier to have that visualization of, okay, one's going to cross here and the other one's going to cross here. Here, they both are same, so we're getting those specific values, if that makes sense.
So now that's all visual, but you guys probably want to know about doing the math itself, because that's probably what you're going to be doing on the exam. So to do the math itself, well, first let me highlight this expression here. We can see that this is an infinite sum of a bunch of direct deltas. And I know one of you, I think it was Keith, mentioned getting confused with all the different variables. We have a K, a capital T, a lowercase t. What are all these different things? Well, the T is your t-axis, your real number line in the time domain, at least. Your capital T is a constant. That is your period, which is defined in the problem. For this particular, for B, 223B, T I think was, I don't know, it was like 2 or something. Oh, it's 4. And then K is an index. Now, the neat thing about indexes is that they are only integers, whole numbers. So K from -infinity to infinity does not include 0.5, pi, irrational numbers, and it only includes 1, 2, 3, 4 to infinity. So that that's why I refer to it as an index. It's what sum am I on? So when we start the sum, usually as humans like to start at 0. So when my period is 4, because that's a constant, I can't change that. At what point on the t-axis and at what k value will proc this direct delta to an argument of 0? Because we know from the definition of direct delta is only a non-zero value when the things inside the parentheses are 0. So if I want to figure out when the argument equals 0, I'll just make that equation. T minus k big T equals 0. Solve for T and K. So as we traverse the T axis, we're going to try every single T in infinity. What K's happen to line up such that T minus K big T equals 0? So K's can be integers, so we'll start at 0, 1, 2, 3, and solve, and then solve for T. Anyways, this is going to be such that you have spikes equally spaced by T starting at 0. So 0, 4, 8, 12, 12, 16, so on and so forth. So whatever that T value is, you just know that this sum procs this direct delta at evenly spaced intervals of T. Anyways, now that you know that, the next step is to actually write the convolution. So here we write the convolution, then we write the definition of the convolution, and then this next step here utilizes the shifting property with the direct deltas, the fact that something convolved with the direct delta returns that something at that same shift. So that allows you to put this H in for this direct delta, and that's what we did here. So now, mathematically, we have an infinite sum of this triangle pulse evenly spaced out at this period. And that's all the math there is to it. You don't have to trudge around with, limits of integration or, I don't know, product rules of exponents or any other weird stuff. And that's the reason why this problem gave you a picture of what H of T was and didn't tell you what the expression was. If you wanted to write this down mathematically, you would have to have a piecewise function of one line with a negative slope and another line with a positive slope to find at the intervals. And piecewise functions are ugly in math. So why deal with that when you can just, skip steps, I guess, and just write it down like this. Do we have any more questions? For this? Does K go to 1, then 2, then 3? Yes. So, but when you're traveling through all your Ks, the only time you actually get a real output is when the whole inside the parentheses is 0. So first off, if you want to think of this as an algorithm, you're traversing the T-axis. Pick a value for T, then enter this operation, this infinite sum. So from the perspective of this giant sigma, from this sum, T becomes a constant. But we know that we're working with a function of T, so T is not constant. It's only constant every time we do this infinite sum. So I'm going to pick a value of T. I'll pick 2. Because right now I want to plot, maybe I'm plotting this by hand, and right now I've already plotted 0, 1, and 2, and all the points between that. Right now I'm at 2, so I picked T equals 2. So little t equals 2 minus K times big T, which is 4. So T equals 2, big T equals 4. And K becomes our independent variable. Stop capitalizing. From the perspective of the giant sigma. Infinite series giant sigma. All right, so you write that equation equal to 0 and solve for k at that point. So 2 minus k times 4 equals 0. Solve for k. Well, in this particular instance, I picked 2 on purpose for t. I would go through t equals k4. Well, then I would divide by 2 divided by 4 equals k. However, k cannot be a partial number. 2 divided by 4 equals 1/2. But that's an illegal value for k. K must be whole numbers. It must be integers. So we cannot provide a solution for when t equals 2, and thus it must be 0. So when I'm plotting my graph by hand, at t equals 0, this function is 0. I'm sorry, at t equals 2, this function is 0. So let's move on to t equals 3. Well, the same thing is going to happen. I'll just zoom right ahead, and it becomes a fraction again.
And to answer one of the questions on the side, k can be a negative value.
Yes. Yep. Yeah, because you're going from.
It just has to be a whole number, basically. You can't have fractions and anything or partial fractions. It has to be a whole integer.
Yeah. Now, when I chose t equals 3, same thing happened. I got a fraction. Now let's see what happens with the magic of 4. T equals 4. You can see right now it's going to be something cool might happen because it matches the period. So t equals 4, t equals 4, t equals 4, and thus k equals finally an integer, a whole number. That's when the direct delta procs, and its argument is non-zero. Or I'm sorry, its argument is 0, and therefore it outputs a non-trivial output. The output being 1, or whatever the height of the function you're shifting it with. So now we just keep on the t-axis, do this again. This will produce another unsolvable case, and I'm not going to keep going through. I'm just going to skip ahead until the next time it procs, and it will proc at 8, a multiple of the period. So this becomes solvable again, and we get a whole number, and k equals 2. That's your whole number again. And then you can keep doing this off to infinity. If I chose 9, again, this becomes unsolvable, so on and so forth, and this becomes a fraction, until I get all the way up to 12, because that's a multiple of 4. It's, 4 times 3 is 12. And so I know if I plug in 12, this should come out to a whole number again. So on and so forth. Does that make sense? So that's how you I guess get through that problem. What problem were we on? Sorry, it's in front of me. Here it is. Nope. I scroll down. Hold away from it. At least 2 problems. So anyways, did I answer everybody's questions about that? John's question was answered about negative k's.
I think you did. I have a quick question I just thought of.
Okay.
And this is more logistics. So regarding when we're actually taking our midterm, I know that having taken other classes, it's recorded or they have a video monitoring for it. How stringent are they on your workspace? Because, for example, my workspace, I've just moved here. I share it with both of my kids and my wife. So I've got a printer, 3 other laptops, lots of stuff. I can move the stuff or cover the stuff up, but how pristine, spaced out, cleared out do I need to be prior to sitting down to take the quiz?
I would definitely make sure you don't have any of the other laptops going or within camera view, just to kind of allow that way that no one rewatching that video thinks, could he have possibly opened those laptops? And then make sure there's no other textbooks and things like that. I mean, if you have a history textbook up there, I mean, I think you're probably going to be okay. My best advice would be to keep it as clear of textbooks, papers, or actual electronics as possible. Your printer should not be an issue. Other than that, that would be my best bet. I don't know what Woody thinks on that as well.
I would not recommend having a history book or some non-class related textbook on your desk. Your desk, your workspace in front of you, in front of the monitor, should be completely clear of everything except your cheat sheet, a calculator, and scratch paper, pens and pencils. Everything else should be put away. I mean, your printer, like, you know, Mallory's right, the printer itself will not be an issue, but I would not recommend any other text, any other words, nothing else. So when you first start your RP Now session, the first thing it does is, you know, well, it has you log in, and then it authenticates you. You have to show it your license, your driver's license, your ID, and then it takes a picture of you, and then you pick up the camera and show it your entire desk, and show it the walls around your the area that you can see. Because if you have a poster on the wall by your desk that has all the answers, you know, that's illegal. Or having another cheat sheet, that's illegal. So
go ahead, sorry.
Oh, and then you scan the walls by your desk. You scan the room to show the exits, indicating that the doors are closed and that nobody will be entering the room during the testing process. And then you show it whatever items on your desk that you are allowed to have. So show it front and back of your cheat sheet. Show it the front and back of your calculator. Show it what type of calculator it is, because sometimes I forget about this class, but some professors limit what types of calculators you're allowed to use. And yeah, that's the gist of it. Show it your each and every sheet of scratch paper, front and back, to show that they're blank. And that's the process. And then nobody enters the room while you're taking your test.
And when you're doing that room scan, just make sure you do it slowly so that it's everything's visible. You don't want anything to be mistaken as something else. I mean, a lot of times when I'm taking my exams, they're in one of my kids' rooms, and there are cameras in my kids' room so I can see what's going on if I'm not in there. I will take those down. My youngest has a baby monitor in his room. I will take that down, make sure those are off so no one can kind of interrupt you accidentally, or that be mistaken for a way to get that assistance. But it's definitely important to have it as clear as physically possible. You don't want anything that could be mistaken as you cheating on an exam.
That goes so the RP Now session, obviously the camera's watching you. The camera can't pan or zoom or anything like that. So at some point after you showed it at your desk, the rest of it, it'll follow your eye movement, and it can see your mouse on your monitor, so it knows what you're doing on your computer. But beyond that, if somebody enters the room and interrupts or something, the microphone's listening the whole time, and that is where a lot of flags come from. So I know the last couple of semesters, because there's an RP Now update, a lot of students will talk to themselves as they're reading a problem aloud, and that's an issue when you're in a brick and mortar school and students are around you trying to take a test too. But it's not so much an issue when you're by yourself, except that default rules, the algorithm in RP Now, if there's audio of any kind above a certain level, it will flag it, and then the professor will be notified to review the video to make sure that you weren't talking to somebody or had an earbud in your ear or a microphone in your collar or something weird. And if you're just reading the problem out loud, it can hear what you're saying and see that you're reading it on the screen, and obviously the professor knows what problems there were too. But yeah, be careful for sounds.
I can tell you, as far as the reading to yourself problems, I get flagged almost every single semester for that. I'm notorious for doing that. It's one of the reasons I do not take brick and mortar classes. It usually just gets reviewed and it's fine. The other thing I have had happened, I have little kids. They don't always understand. I have had one of my kids barge in while taking an exam. I just politely explained to the camera, it's kind of weird to do it. Just let them know, sorry, that was my son. Get them, or daughter, get them out of the room, and just let the camera know that what that was, so that there isn't that little mix up of them thinking something's going on. Again, you're going to get flagged. Again, the professor's going to review it. They're going to see that, especially if you make that explanation in there. I've also had a test freeze on me in the middle of the exam, and I just started talking through what I was doing. Okay, my screen is frozen. I can't see this question. I can't scroll. I'm going to exit out of the test. I'm going to relaunch that test, and they're going to see those, you know, 1 or 2 minute breaks in between if something like that happens. Obviously, you don't want to do that if nothing is going on wrong, but if you have to for that reason, just explain it. And then anything for any class, always, if something goes wrong to where you had someone barge in, always email the professor. That way they kind of have a heads up of what's going on, and they don't think that there's been time to make something up, things like that. And then Keith, to answer your question on the scanning your work during the RP Now exam, it kind of depends on the professor. I know most of the times it's explained in the midterm information section or final information section. Most of my professors I've had before have given you like a 10 to 15 minute window after the exam to get it submitted, to take pictures and upload those pictures. I personally usually exit out and then scan and upload. But again, that comes down to the professor, and I cannot remember what Dr. Wang prefers, but I will look that up for you and let you know.
Well, I already know. She prefers that you scan and upload during the RP Now session, but after the exam's over. So in the RP Now browser, you'll finish your exam or a timeout or something, and then it'll go back to the normal Canvas shell, but inside the RP Now browser. RP Now is still active. The camera's still watching you. But then you can navigate in Canvas just like normal. Go to the exam submission link. You can also, you know, utilize, if you can see my screen, you can utilize the start menu and go to programs, and like maybe you have, like I do, this little software here for scanning. My scanner is out in the living room. After you've submitted the exam, but while you're still in RP Now, all of the requirements are moot. You can get up, you can talk, you know, you can. You know, obviously, I just mentioned my scanner is out in the living room. I leave my room, go out to the scanner, scan my thing, come back, wait for it to finish, open up this program, you know, save it to my directory, you know, to a folder, do all that stuff while the camera's still watching you. Dr. Wayne prefers that she can see this entire process on the camera. That way, she confirms without a doubt that you have not continued working on the exam on your sheet of paper after the exam it closed out on the monitor, on the computer. Does that make sense? So now, as Mallory stated, if whatever technical issues, if there's some kind of technical issue that arises where you can't scan during the RP Now session, if you end up closing the RP Now session and then scanning outside of, you know, recording, the world will not end, but the professor, you know, it's gonna be up to her whether she wants to, you know, make you take another test or whatever. Just keep that in mind. Try to scan while you're still being monitored by RP Now. And there's many ways of scanning. You can use your camera phone to take a picture in a scan app to convert that picture into a PDF, and then you email it to yourself, or you can do that, and instead of emailing it to yourself, you upload it to one of your cloud storages. So like, for example, on my desktop, I have Google Drive here. So I can scan on my phone, put it on Google Drive, because obviously that's an app on my phone as well. It will go through the cloud, and then I just pull this up, let it refresh, and then pull up my exam that way. And that way you don't have to email yourself to yourself. Because one thing RP Now does not let you do is open up a separate tab to go to your like personal email account. If you're in Canvas, you can go to your ASU email. I personally don't use my ASU email, so I have to use my personal one. So I end up using this cloud storage technique.
Another one that I like to use is an app called Cam Scanner. You can download it on your phone and open it on the computer. How I usually do it though is I will take a picture with my phone on Cam Scanner. It compiles it all into a single PDF, and then I actually keep the file downloaded onto my phone right then, just for the speed of things. 20 minutes is a long time, but it always seems to go really fast and make me nervous, so I try and make it as quick as possible. So I take those pictures that I need on the cam scanner, I save it as a file, then I actually open the Blackboard or Canvas on my cell phone, and I upload it from my cell phone is usually how I do that. It seems to kind of go faster. You could save that PDF into Google Drive and then open it that way as well. But that is another option, and you can open cam scanner on the computer as well.
Yeah, so there's instructions on Canvas that Dr. Wayne wrote for how to upload your scan. Those are suggestions, or I wouldn't even call them recommendations. They're just the first technique that she thought of off the top of her head. But if you have another way of scanning something, a scan is a scan, and RP now watching you scan it, that's all that really matters. It just matters that you're not working on the exam after it has submitted, but before this submission link has expired. Makes sense.
And then James brings up a really good point. Canvas is not like Blackboard when it comes to taking your RP Now test. When you go into the Canvas course module, you actually need to go to a section that will say, like, take my exam. She should link it in there. You want to download RP Now from there and go through that full process, because it will save the name of the exam you're taking and it'll save your username, and it makes it so that you're able to find the test and kind of a straightforward process. So don't just if you already have RP Now downloaded, don't open it through there, because a lot of times you can't find the exam unless you go through the Canvas module link itself.
That's true. However, there are two different RP Now download files. One of them only works with Blackboard, and another one works only with Canvas. So while what Mallory just said is the easiest thing, if you do have access to the RP Now install file for Canvas specifically, and you open up that one and not the one for Blackboard, you can navigate to your class without doing that via Chrome or Internet.
Oh, nice.
Yeah.
I did not know that.
It's weird because the two file names will have similar names, and you can't tell which one's which. You just have to keep really track. So like on my desktop, I have them here. So I put them in separate folders so I know which one's which. If I'm in a class, there are no classes at ASU with Blackboard anymore. Well, very few at least. So I'll probably never need to use this one again. But this one, when I open it, that's the actual file, install file. And when you double click this and your computer installs it, it creates the exact same icon as if you had installed the one for Blackboard.
I have a question about the time on the tests. Can you visually see that as you're scrolling through, or do you have to keep scrolling back to the top to see the time left?
It will have a timer up in the right corner. And if I remember correctly, you do have to scroll all the way back up to see it. The timer itself doesn't travel with you. However, if you can see my screen, the clock is down here in the right corner at all times if you're on Windows. On Mac, I think it's at the top bar on the right as well. And so just when you start your exam, take a note of what time it is. And then that way, it might be a quick reference as well without having to scroll all the way back up. Now, that being said, sorry, what?
That is so distracting when you have to go all the way back to the top to see how much more time you have. And
I agree. Now, that being said, this particular exam, I don't think there's that many questions. I mean, there's a lot of subparts, I guess. I'd have to look at it again. But anyways, I don't think you have to scroll very far to get back up to the clock. So that's one little benefit of this particular midterm.
Okay.
John, you were writing about using Tiny Scanner and Dropbox. That's exactly what I do, except for I use Google Drive instead of Dropbox. So what you've done before with Tiny Scanner, you can do again. Well, let me clarify. If you're going to be using cloud storage, you need the native file explorer for that particular cloud storage already installed on your computer. Because you won't be able to open up a new browser tab to get to your cloud storage. You have to get to it via Windows native file explorer. You know, so like on my computer, since I went to Google and I installed this ability to see my cloud storage, when I go to my computer, you know, my PC, cloud storage pops up. Well, I have to go to C and then go to my desktop or whatever. And then there's cloud storage right there. So from the perspective of RP Now, I can't tell the difference between a folder that's cloud storage and a folder that's native on your desktop. A folder is a folder, you know, from the perspective of Windows. But RP Now does not like opening up new Internet Explorer or Chrome.
No.
Yeah. What else did you write? Let's see. So there's going to be an issue opening up Microsoft Word. You should not be you cannot open up Microsoft Word. I don't know why you would need to. I guess it's not a PDF.
That's why. Excuse me. That was my concern. I haven't used the PDF, the scanner to create the compiled PDF. I take Dropbox individual files, and then throw them into a Word document that I then print as PDF. That's how I've been doing it for all the homework uploads and stuff like that. Okay. That's why I was like, I don't know how to deal with this. This is more advanced than I am used to.
Well, so I have Tiny Scanner, the exact same app. Now mine's the paid version, so I don't know if maybe I have a paid feature, but my Tiny Scanner app takes my pictures and converts them to PDFs directly without any issues. So it sounds like that your Tiny Scanner does not do that?
I am not sure, to be honest.
I'm almost fairly certain that Tiny Scanner converts to PDF, and then you would be putting the PDF of the scan into your cloud storage, and you don't have to mess with Word at all. If it doesn't work for the unpaid version, I will just go ahead and buy it, because I think it was only like $5 or something.
Either that, or you could get the CAM scanner, which is free and will convert it to a PDF right away.
Yeah. Yeah, it's a good point. Is all this stuff needs to be figured out before you sit down to take the exam. You must, and I'm not saying must as it's a required thing to pass the class, but to feel comfortable taking your exam, you definitely should be going to the RP Now practice exam, because it will allow you to test your entire system. Whatever process you want to use to upload your scans, the practice RP Now test allows you to practice it, to go through the motions and see what will work and what will not work. Do that stuff today. Don't do it tomorrow when you start the exam.
The free version does work. I just tested it. Thanks for the advice. So I can just scan each of the documents, my notes pages, upload it as one file. Is there a naming convention? Do y'all care?
No, not for the exams. I personally have a naming convention because I'm like OCD, I guess. But I don't think the graders care, because they'll see that,
it's attached to your account in the Canvas, and they can see who submitted it and what time and stuff. So unless it says in the exam information area, please name it this, you're fine with naming it anything. I'm with Woody. I have very specific naming conventions for homeworks and exams, just because I have the same issue, but I don't think the graders care per se.
Just to add one more little piece of information for John with Tiny Scanner. Tiny Scanner will allow you to take multiple pictures, i.e. multiple pages, and keep them as one PDF. Just be careful with that, because when I first started using Tiny Scanner, I guess I didn't really know what I was doing, and I was making separate PDFs for each page. You cannot upload multiple PDFs for each, one PDF per page. So make sure you're utilizing the button. And I can't explain it unless I see it in front of me. And I can go through it, if, step by step like that if you want me to, but I won't unless you ask me to. But yeah, you can take multiple pictures, one for each page, and then that will go to one PDF. Yep. Okay, cool.
Did anyone have any other questions or concerns about the exam or anything like that?
So out of curiosity, on the practice 3.34A this week, what does the 3-dot triangle with T mean?
3.34A. Almost there. Going halfway down. 3.34A. What is the triangle? Is that what you asked?
Yeah, the triangle with the 3 dots.
Yeah.
Oh, that. Oh, that means therefore or because of or ergo, something like that. It's just a Latin thing. So let me read it. X of t equals sigma of that junk. Therefore, the period is 1. Oh, yeah. Therefore, the period is 1 because we have a 1 in front of this n. It's invisible, but it's there.
I got the T equals 1. I was like, I don't know what the 3 dots is. Is this a mathematic operator that I need to know because I'm rusty?
It's a mathematical notation. It's not an operator.
It's basically just a way for you to indicate, like, if instead of just slapping down T equals 1 on there and the professor going or the grader going, well, how did you find out T equals 1? Instead, you could put those 3 dots and say, with that equation ahead, and say, because it's this, therefore I know the period is 1, or things like that. If it's just kind of an assumed situation of, we know the period is 1 because of the fact that Woody explained, and there's no actual math that went into finding that answer, you could just add those little dots in there to kind of let them know, okay, he understands that that's where the period comes from.
Yeah, here it is. So what I just did, hopefully you guys can see my screen again. I just Googled, what did I Google? Let me go back. I just Googled math symbols. I went to the first link. And this is a bunch of symbols that mathematicians use in their day-to-day lives. And it's a whole bunch of symbols. So I scrolled all the way down past, I went in, here's logic symbols. Now it depends on context too. What type of math are you working with? Sometimes symbols are shared between disciplines. In logic, the triangle dots is therefore, means therefore. If it's upside down like that, it means because of or since, which is in my mind the same thing. But in the mathematician's world, I think there might be a very subtle difference between those two. Anyways, you scroll through this list. There's a whole bunch of symbols that you might not have seen before, and a bunch that you have seen. So like here's our beloved convolution. Sometimes the asterisk means just straight up multiplication. Here the asterisk means the conjugate of. In this context, is convolution. Anyways, yeah. I invite everybody, all students, to look through this list at some points, just gee whiz, and see what types of symbols are used. Because the higher up you go in the degree plan, especially if you get to grad school, professors will use this stuff and not care if you don't know what they mean. They expect you to look it up on your own, or to have, already know what it means.
And it's very easy in some of these classes as you get higher up there to think that that symbol means something and realize that it's not specifically in the context of, say, a convolution. It should be a conjugate. So it's very easy to kind of mix those up. So I, like what he said, most definitely find a page that you can bookmark that's easy to get to kind of check that. You can also do that with constants. I mean, even now in some of the classes I'm taking, every now and then I will mistake a constant for a different type of constant because they're the exact same letter value, but two different types of subject material, they mean different things. So it's definitely important to have something like that to reference.
Here's a good set of symbols that a lot of people use, but weren't explicitly taught. Like I see this all the time in my math classes. Well, I don't take math classes anymore. Anyways, you get what I'm saying. And I have to look this up again, but this is set theory in math, this math discipline of set theory. We see these little symbols. When we talk about piecewise functions, these symbols are really important. Although most of the time at lower level courses, you just say it with words, with human words. But once you get higher up, you won't see human words anymore. So like A, upside down U, B, and that's not a real U, by the way, it's just a curve, means the intersection of this set, you know, or with this one, it's the union of. And so like, so this upside down one means when does the set of A and B share the same numbers?
You will see that stuff Woody just showed you all over every moment of 350. So if you've not taken 350 yet, most definitely find that as a resource because those are extremely important for 350.
Yeah, here's a symbol that we learned from digital design fundamentals. We use this symbol as an XOR. In this context, it's not an XOR. It's a tensor. Anyways, that's just anyways. Here's some constants. But yeah, I won't beat that down. Look on your own. All right. 350 math or engineering? 350 is engineering with a lot of math. Thanks for breaking down. Yeah, no problem. I actually haven't taken 350 yet. I'm taking it, I think, next year.
Yeah, that one was interesting. Let's just go with that. It is definitely, like James just said, it is a stats class hidden inside an engineering course.
On on the practice problem 3.37a that was given this week, there was a limit in there that it had the two summations, right? Isn't that what the sigma value is? One was 0 to infinity. The other one was negative infinity to 1. Why did that one not go negative infinity to 0?
Oh, that's a good question. So one of the good things about, well, let me back up. One of the things you want to do with these sometimes is get them into a form that you can use the geometric series on. So just a quick reminder what the geometric series are. There's a whole bunch of geometric series, by the way, and you learn a bunch of them from the end of Calc 2. But in this class, we've only used one, and thank God, because geometric series suck. But this is the geometric series. Whenever you have very specific infinite sums, they converge to a not infinite result. And different expressions will have different convergences. Not everything can converge, but a lot of things can. Anyways, the one we use a lot in this course is it's just the one of this form, a base where the base is less than 1, absolute value of less than 1, to the kth power will always converge to this expression 1 over 1 minus alpha. So anyways, when you have a problem that happens to make you go from negative infinity to 0, Well, since this is a sum, you can add them in any order you want. You don't have to go from negative infinity to 0. You can instead go from 0 to negative infinity. You're using the same values. In algebra, summation or addition is, what is it, commutative? You can do it in any order is what I'm trying to say. So with that problem, what problem did you say it was? Week 3?
3.37a.
So with this problem where you're going from negative infinity to negative 1, you know, they probably wrote it originally, oh, here, they wrote it as negative infinity to infinity. So they broke this up into 2 summations. You're doing the exact same summation. A summation plus another summation is really just the summation. So they broke it up from 0 to infinity, and then from negative infinity to negative 1. They stop at negative 1 because you already covered 0 here. And that allows you to count everything. Because remember, n, just like k, is an index. It's an integer. It must be a whole number. So anyways, that's how you cover all of them. What this allows you to do is you put this one into the geometric series form, which converges to an actual number, or a single expression. And then this one you just manipulate differently. Now, the way you manipulate this one, which you can see in the subsequent steps, it does that, is you want this one to also be in the same form, n equals 0 to infinity. How do you do that when you have a negative infinity to negative 1? Well, we know that our base is 1/2. Well, we know that we can just flip this. Anytime you flip a fraction, it's the same thing. Well, I skipped a step. When you flip a fraction to an exponent, let me say it again. When you have a fraction to an exponent, that is the same as the fraction inverted to the negative exponent, the same negative exponent. Does that make sense? I'm saying it in words, and maybe it's better if I write it down visually, but does that make sense so far?
I get your words. I don't understand the logic where, I mean, we've gotten used to the one way of looking at it, and then at this step, the one that you're highlighting, it seemed like they flipped a bunch of things for some reason, but not necessarily. I'm like, what?
So I actually highlight this in my the thing that I posted up on Piazza, my personal notes from the midterm review, and I'll have to scroll through it to see what problem it was. But I have notes that for every single step of this that explains it, like, step by step. And let me try to find it, and then I'll highlight, where it is, what problem it is. I'm gonna. Maybe it was on the final review that I did that. I hope not.
If this is something that's already been covered in the Piazza notes, please don't go back over it. I'm still working my way through the Piazza notes. Unfortunately, since I've worked during the week and parents and stuff like that, I have to cram all of my paperwork into the weekend. I just read and watch videos during the week. So if it's already been covered and it's something that I should be able to find, then I don't want to take up other people's time if they've got other questions to go through.
I totally understand. I don't know if it was on this particular review sheet or not. That's why I just wanted to find it real quick. But it doesn't look like it is. So we're going to go into the future now and look at my final review. And you don't need to worry about the content that you haven't learned yet. I just wanted to highlight this one thing, because it is important. You're right, and it wasn't very well covered in the lectures or the the homework and stuff. But yeah, the idea is that if you're doing a sum, you can do a sum in any order you want. Then the next step is, if you have a sum using negative n's or negative k's, you can just flip the sign. You can invert the fraction and flip the sign of the exponent. That's all you have to do. And that's the same thing as using positive values of n, because the negative sign is now on the exponent itself. You don't need to put it in the, the limits of the sum to be redundant. Yeah. Kind of losing hope for finding it, so I don't want to waste people's time either. But yeah, I mean, let me see if I can just write it, because I've lost hope that I'm going to find it. If I wrote oops, 1/2, 1/2, and hopefully it's big enough on your screen, but down here is where whatever I type becomes the equation. So pay attention to that. This is the same thing as 2/1 to the -2. So if I plug this into my calculator, whoops. If I plug this into my calculator, 2/1, I picked a bad example. Anyways, plug into your calculator the quantity 2/1 to the -2 power. Whoops, that's not supposed to be 2, that's supposed to be 1, I'm sorry. This is equal to 1/2, because you invert the fraction, take the negative exponent, and that's the same thing as having a non-inverted fraction with a positive exponent. What this allows you to do is, in this problem, utilize positive values of n. Because we want positive values of n so that we can use the standard geometric series that we used on this other portion. I don't know where this e of j omega came from, but that's not important right now. So the step where they invert is where it becomes important. Here's where they invert. So it was, nope, that's not right. We started with 1/2. Oh, I'm sorry. You don't need to invert if you're just adding, if you're doing it with the exponent. So, no, that's not right.
I believe that one has to do with the fact that the h of n has an absolute value of n function.
Oh.
So you have to split it from 0 to infinity for those positive values of n. And then you have to do negative infinity to the -1, since 0 is already included, for those negative values of n. So you have a summation of the 1/2 to an n value, plus a summation of that 1/2 to a negative n because of that absolute value. You need to include everything.
Yeah, it would help if I, knew what the whole problem was asking for and stuff to get context. But anyways, the point is, whenever you have negative infinity to some negative value, you can just flip the sign of the exponent and then go with positive values, because that information is now encoded in the exponent itself. Then, from this step to the next step, you need to add in, or rather subtract, the n equals 0 sum. Effectively, be doing that twice. So if you're going to be, if you want this one to say n equals 0 to be able to use the geometric series, so you need to make this 1 turn into a 0, and then add another term in front of this that subtracts that out so that you're not counting it twice. Does that make sense? And then you'll have this completely in a form where you can use the geometric series.
It does make sense. I didn't see that step in there. That's why I was like, some
Yeah.
of the shorthand. I think that I was not grasping the flow of logic.
It does certainly look like they skipped a step here. I'm trying to see if they hit it in here. That's probably what this is. But I promise it's in there.
Yeah, that's what that e to the j omega over 2 on the outside is. They basically pulled one exponential factor out of that.
Yeah, because when n equals 0, well, what is this whole thing when n equals 0? Well, it's just 1 times that thing. There's no n. Well, never mind. It also helps sometimes, and that's probably what I'd have to do to fully grasp what this statement is sometimes just expanding the first few terms of your infinite series helps you visualize what it's actually doing at each value of n. So if I had a piece of paper in front of me, I would write, well, the first few terms. I would say e to the j omega over 2 to the 0th power plus e j omega over 2 to the first power plus e j omega over 2 to the second power, so on and so forth, just for a few terms, just to see what it's actually doing. And then you'll probably be able to see that there's a common, what do you call it, a common multiple that you could pull out, and that's probably what this is, because you multiply this by every term in this infinite series, and it will get you, well, it'll get you that, I guess. It'll get you something related to this problem. I'd have to see it to be able to really point at it, but.
How far simplified do they prefer that we get this? Because for me, I probably would have taken the e to the j omega times 1 and then multiplied through by the 2 and been like, oh, that seems fairly simplified. But I see that they continue to trim it down more and more.
Oh, you're talking about from this step to this step?
Yep.
I mean, honestly, if this were like a multiple choice exam where you had to input a very specific form of the answer, well, I guess it's partially easy because you can see what forms they are asking for. But we have a human grader, so you don't need to necessarily worry about that. The human grader has a brain that can understand context, and they're not just in the very beginning of grading your paper. Yeah, they're looking just at the answers and then only highlighting the ones that were wrong. Then they go back through for the ones that were wrong. They actually look at your entire body of work for that problem and look at context. And if they get to the end of your problem and they see that, oh, you just didn't take the very last step to get to the same form that they have on their answer sheet, but it's still the correct answer, they'll mark it as correct. They might take away a half point or something, maybe if it was like, if you had 5 steps to go to simplify it, but in the end, a correct answer is a correct answer. And whatever form you choose as elegant for your eye, well, who cares? It's still the same answer. Does that make sense? Within reason, obviously, it's a case-by-case basis, and it's all context-based. So it just depends on the particular problem, what form the problem asked for, what form you put it in. Sometimes you can just stop at the complex exponential form, like when you're looking for Fourier series stuff. You can just stop at the complex exponential form. Sometimes there's not a need to convert it back to a sinusoid, and you will still get the same amount of points.
One other thing I think about the practice questions.
I was just going to say, but if the problem statement itself says to put it in a very specific form, then you're limited, and you have to go with that form.
Sure. One of the other things I had about the practice questions for this week was there was a number of times, 3.34a, I want to say 3.36a, a couple of them in a row, where you're at one right now, where they graphed out what the magnitude and plot and phase
Yeah.
were. Is that a necessary step? I guess I'm not grasping enough. It seemed like we could just go through the determining the H function, et cetera, I was trying to figure out why those were included, or if I'm missing a piece that I should be grasping.
So actually physically graphing them, I'd have to look at the exam, but I don't think you're going to need to like actually make these two plots here, the magnitude and phase. Now, understanding what they are, definitely you need to know that, especially for future courses. So any expression ever in all of existence that has a complex exponential in it is really two pieces of information contained in one entity, if that makes sense. So anyways, a complex exponential has a magnitude and phase. All complex exponentials have magnitude and phase. And to understand this, you need to review complex numbers, which Dr. Wayne actually posted a really cool document for in week 3, I believe, named complex numbers. And if you wanted to, by hand, calculate magnitude and phase of an expression, you're plugging in your values for each point on the graph and then manually calculating them. This is how you calculate the magnitude and phase. First, it's rare in this class that we see complex numbers in rectangular form, but this is how most people are comfortable seeing complex numbers. In electrical engineering, we most often see it in this form or this form, which is what we see in this class a lot, is this exponential form. To calculate the magnitude, well, it sucks because you have to convert it back to rectangular form, which means that you just separate the real parts from the imaginary parts, group them into separate groupings, and then whatever all of your real parts, get it into, make it one thing, I guess. Like if you have two numbers, you add them together to get A, and then you plug it into this expression here. And then you do the same thing for the imaginary part, and you plug that into here. And then you take the squares and then square root them, and then that becomes the magnitude. And then same thing with phase. After you've determined A and B, you just put them into the arctan function, and then hit go, and your calculator will spit out a degrees. When you do that, though, pay attention to whether your calculator is in degrees or radians mode, because that will be important on how you write it down on your piece of paper. Now, also, you don't have to use these formulas if you don't want to. If you have a graphing calculator, there's actually buttons that do these for you. On my graphing calculator, you just plug in this entire expression, not worrying about separating real parts from imaginary parts, and you would literally just hit the magnitude or absolute value of button, and then the phase button. And I would hope that most people have TI-83s or TI-83 pluses. So if you have those calculators, what you do is you hit math, and then you scroll over to CPX, which is complex plane. And then you go down to number 5, which is absolute value of. The absolute value of a complex number is the magnitude of that complex number. It's the same thing. And one other note about what the absolute value of is in magnitude of a complex number is, that's the same thing as the length of the vector that's drawn in the complex plane for that point. And that's why you see this square root. Because you're taking the distance. You're taking the distance of 2 points. The distance that those 2 points are apart from each other, from the origin. Anyways, through understanding when you have a calculator and have the calculator do it for you, back to that, you go to math, scroll over to CPX, and then number 5 is absolute value, and number 4 is angle. Angle is the phase. And you just plug them in and hit go, hit enter, and it will tell you exactly what they are. That's if you have, just a number complex form. If you have a function in complex form, you can't just plug that into your calculator. You'd have to do it by hand, and that's what these formulas are for. So that's how you plot those two graphs. You go for every single data point, one at a time, and you calculate these magnitudes one by one, and you plot them, and then you go through every single data point and plot these phases, and then make those graphs. That's how
I don't believe for the midterm you're going to have to graph any of those. A lot of the times those graphs that she has you do in MATLAB are just kind of so you can get that visual of what's happening, and so that you have that understanding of the magnitude and the phase being a portion of that function.
Yeah, you'll be doing a lot of magnitude and phase plots in your Circuits 2 class, a little bit in Circuits 1 class. There's a handful of senior level classes that do it. Signals, Systems and Signals 2, which is EEE 304, will definitely have you do this as well. So if you plan to move on in those types of courses, you're going to need to know how to do this. Not too important for the midterm, though, just as Mallory said. Also, pay attention to if you're in radians per second or, well, angular frequency versus, what do you call it, like rectangular frequency? Hertz versus radians. Hertz is cycles per second. Radians is, or omega, angular frequency is radians per second.
Chris, to answer your question on reviewing the material, quizzes are helpful, very helpful, kind of give you an idea of what's being deemed important. Definitely go through those, figure out, how to get those answers if you missed questions and you on both attempts. Those homework problems, I definitely recommend checking those out, making sure you can work through all those as well. And then that midterm practice review. Those are the biggest things, is just kind of going through each and every one of the problems, making sure you understand how to get to those answers, making sure you ask any questions on those prior. That way you have an idea of how to work through all those. I wouldn't worry too much on memorizing the equations, because you have that cheat sheet. You can put those in there. Having a good idea of those equations is always helpful. But the biggest review help is definitely reworking those problems, taking the time to go through them and make sure that you can consistently get those correct answers. Yes, Chris, I believe the online midterm opens on Sunday and closes on Monday. Let me verify that for you. Yeah, so the midterm, Chris, will open Sunday, June 9th till Monday, June 10th. Or through Monday, June 10th. Yeah, Chris, it looks like it opens June 9th at 12 a.m. and closes June 10th at 11:59 p.m.
Tempe, Arizona time, by the way.
Yes, and that is Arizona time. Were there any other questions?
Just to fill the dead space while people think of time or questions, I'm sorry. That's not what I want. I have this cool little look ahead for the rest of the course and how, like, the forest for the trees. Just to make people comfortable, I guess. It may be comfortable, I guess, but I'm weird. So here's all the major topics that we learned in this class. This is mostly stuff after the midterm, except for 4-year series. So the reason why this class is important, okay, so the first week is a bunch of background information, some terminology and like notation. The second week is convolution, which is used for everything in the rest of the course. And then the third week is the most important, it's really when the class starts, to be honest, 4-year series. And that introduces you later to Fourier transform, Laplace transform, and Z-transform. Now, the reason why we learn Fourier series and Fourier transforms, a Fourier series allows you to characterize a steady state frequency analysis of a periodic signal in continuous or discrete time. So that's the important reason. We want to look at the frequency analysis of a signal. What does it look like on a spectrum analyzer, for example? You know, we're used to working on oscilloscopes, but what if we wanted to look at the frequency analysis? We use a spectrum analyzer. Now, for periodic signal, that's what the Fourier series is for. Later in history, they developed the same thing for non-periodic signals, and that's what the Fourier transform is for. So it does the exact same thing. It allows you to analyze the steady state characterization of a signal in a system, or signal or a system, in CT and DT. Then later in the course, well, what if we're not happy with steady state? Remember from your DPQ class, your differential equations class, we talked about steady state when a system has settled. But what if we really need to know about the transients? When you first turn the system on, when you first shunt power into a circuit, or drop power out of it, you have this period of time where it has not settled, or it's settling. Well, if we want to characterize those bits, those parts of the system, that's what the Laplace transform does. It allows you to do the exact same thing that the Fourier transform does, but with a complete description of the signals and systems to include both the transients and the steady state frequency analysis. Now, the Laplace transform is limited to only continuous time. So they invented a thing that does the same thing for discrete time, and that's the Z-transform. The Z-transform is the Laplace transform for discrete time. And that's what the whole rest of the course will be for. That's what you're leading up to at this point. So that's why you need to know convolution and, you know, what direct deltas are and unit steps and all this other stuff. Because we're eventually going to be doing something that we saw before, the Laplace transform, and doing these other versions of it. By the way, all 4 of these things is just a special case of the Laplace transform. I just want to say that out loud because it's more complete than any of the other ones in mathematical terms. I have a cool thing here for stability. Anybody's interested in that? I actually have a whole video on this, on stability alone. Not that it's crazy important for the midterm, but last semester a student specifically asked me to, to write a lesson plan for stability. Go review Laplace transform every chance we get is what you're saying. No, it's going to be spoon-fed to you again, just like it was in DiffyQ. Honestly, there isn't a whole lot new about Laplace transforms. I mean, yeah, if you review now about Laplace transforms, then when week 5 comes around, week 5. No, week 6. When week 6 comes around, you'll be all that much ahead. But if you don't end up reviewing Laplace transforms, when you get to week 6, everything will be reintroduced to you. It's all the same stuff that you learn from differential equations. And the important thing is, if you can do Fourier transforms, you're going to be fine on Laplace transforms.
Do you guys have any, I guess, videos or anything where you walk through more of the convolutions and the Fourier transforms? Because I get the instructional videos are there to explain like the mathematical foundations of it, but I'm still not 100% comfortable with them. So
the answer is yes. So I know you joined late, but at the beginning of this session, I let everybody know that this session is for what's not covered or in the gaps of my other previously uploaded video.
okay, so if it's all there, then I'll just review those. That's perfect. So,
yeah.
Okay, I appreciate that.
Now, at the same time, we can go over that stuff now if you have specific questions.
And Chris, if you decide like you have specific questions or really would like Woody or I or both of us to kind of walk through one or two things with you, we can always do that. Just you and the two of us if you'd like at some point too. But like Woody said, we can definitely go through stuff like that now. But if afterwards at the end, or you just decide there's something that you realize we didn't cover or you think up afterwards, just send us a private Piazza chat and we'll do whatever we can to help you with that.
Okay, yeah, I think I'll do that. I'll review the material more first. I mean, it's getting easier, but I definitely don't have it down cold. So, and I think it would be more helpful for you guys if my questions were more specific and sort of just instead of just general confusion. So, yeah, I appreciate the offer, and if it comes up, I'll definitely take you guys up on that, but I'll review the older material first. So thank you.
No problem.
Yeah, John, are you in the Google Hangouts? Because if you are, and you have time this weekend, and maybe we want some more walkthroughs, maybe we can coordinate just, so we're maximizing time. I can send you a message.
Yeah, Chris, I am.
Okay.
I just joined. I'm the late ad that just joined.
Oh, I just joined last week, so that's good. Now I'm not the low guy on the totem pole anymore. Yeah, no, we'll send each other messages and maybe do another hangout. But yeah, that covers all the questions I have. So I mean, I appreciate your guys' time. I don't have anything else for the moment.
Okay, no problem. Well, I guess that's it. I doubt James is listening. James, you could probably